Hi, welcome to EC&M Tech Talks. This is another one in the series of how-to videos here at EC&M that we discuss everything from codes and standards that we use out in the field, maintenance requirements, how things work, and so on. So today we're going to be talking about some medium voltage cable. Now, this Tech Talk is brought to you by EC&M Magazine, EC&MWeb.com. That's electrical construction and maintenance then. So if you haven't already, you need to go to EC&MWeb.com, and in the upper right-hand corner, there's that drop-down menu. The very first item is premium content. You want to go ahead and sign up for that premium content. It's free, and you'll get access to tons of information, not only in this topic, but from other instructors as well, and articles, webinars, podcasts, and so on. So anyway, go to ecmweb.com, sign up for your premium content. Now today, I'm going to be using the 2023 National Electrical Code, and we're going to take a look at some of the requirements here. There has been some big changes for medium voltage systems and equipment and so forth, medium voltage cable in the NEC for this year. We're also going to take a look, as I said, at the construction and operation of the different components of this medium voltage cable. We'll take a look at the qualifications that the code requires if we're going to install this equipment. We'll also take a little quick look at one of the articles in Chapter 4 on what they call high voltage equipment. So Article 315 is on medium voltage conductors, cable joints, and cable terminations. Cable joints, you and I would probably call splices, but for some terminology reasons, they use the term cable joints in Article 315. Everything's required to be listed. So this cable has to be listed by some nationally recognized testing laboratory, which when we read this information on here, well, I'll read it to you, pretty small, huh? I'll read it to you, and we're going to find out, yes, this cable is listed. Now, as far as what it talks about the cable joints and cable terminations, those don't have to be listed until January 1st, 2026. So with the addition of the next code, that's not terribly uncommon to see something like that in the code, where we don't have products that necessarily meet the UL listing requirements yet, but they certainly expect it to be available for the next edition of the code. So anyway, kind of giving us, I always feel like, a little heads up there. Construction specifications for this cable. Rather than try and read things out of the code, I'm going to read this information right here to you, and then we're going to relate it to the code as we go along, and we'll talk about how this cable is put together. So this is a medium voltage cable. Right now, I'll go ahead and give you a little heads up. I'll unwrap this copper sheath a little bit, and we'll see some different color, I don't know, some almost feels like rubber and some plastic on here and whatnot. We'll see what all that is as we go through it. So let me read some information on here to you. First of all, it gives me the manufacturer's name and logo, which is fine. I call it power cable. And then it tells me UL. It also tells me CSA. So it's been tested by 2 nationally recognized testing labs, Underwriters Labs and Canadian Standards Association, found to meet the testing requirements. So if I install it properly in the field, according to manufacturer's instructions and the National Electrical Code, this cable's good to use. So it's good to go, right? Now, it tells me it's 2 AWG copper. So of course, that is the copper conductor on the end here is sticking out, is 2 AWG copper. It is 7 strands, pretty easy to count, 7 strands. So I could take it back to Chapter 9, Table 8, and I could find out some specifics on the dimensions of each one of those strands. Since it's number 2 AWG, and there's 7 strands, we could find out the dimensions on the individual strands, as well as for the overall conductor itself. Chapter 9, Table 8, back in the code. And so let's see what else it says here. So it's 2 AWG copper, 115 NL-EPR. So NL-EPR, that tells me that there's no lead in the insulation. And the insulation is the white material that you see here. the main layer of insulation, I guess we could call it. And it's a dielectric insulation. It's ethylene propylene rubber, which is a synthetic type of rubber. And it's also called a thermoset insulation. It has some excellent insulation properties as well as physical properties as well. So we see a lot of EPR used. Now, you'll also commonly see another type of insulation on this medium voltage cable, and it might be kind of pinkish or reddish in color. That usually is an indication that there's some type of lead oxide in that dielectric insulation. But nonetheless, this is all white. It is no lead EPR then. And let's see what else it tells us. It tells us that it is, NLEPR, then it says 5 kV, 133%, 8 kV, 100% insulation level. What's that talking about? Well, we're going to have to go into our code book and find that information. And so let's do that. Let's start with Article 315. We'll take a look. There's 4 parts to this Article 315. And part 1 is general information, and we just talked about the listing requirements there. Part 2 gets into the construction specifications. So, for instance, it tells me there's a table 315.10a. 315.10a says conductor applications and insulation rated 2001 volts and higher. And it says that the trade name is medium voltage solid dielectric cable, which, yes, this is solid insulation. And it says that the type letter is either MV90 or MV105. Well, this says on here MV90. Okay, so MV90. Taking a look at table 315.10a, it says that MV90 means that the maximum operating temperature is 90 degrees C on this particular conductor, and suitable for dry or wet locations. And 90 degrees C, that's 94 Fahrenheit. That's pretty warm. It's either a thermoplastic or a thermal set insulation, and we already said it's a thermal setting insulation. And it has a jacket or a sheath or an armor. Well, this has a plastic type jacket over the outside of it. Okay? Now, that's 100. So maximum operating temperature on this cable conductor is 194 degrees Fahrenheit, 90 degrees C. If that's not good enough, if I need a higher temperature application, I can go up to MV105 according to the table. MV105 is good for 221 degrees Fahrenheit, okay, 105 degrees Celsius. So it just depends on your application. As far as the insulation itself, we'll talk a little bit about that. It says it's either, what did we say? 5 kV, 133%, or 8 kV, 100%. Okay, so we've seen the temperature limitations on it. I can have insulation. My insulation can be either rated for 100%, it can be rated for 133%, or it can be 173% insulation. Cable that's rated for 100% with no shield on it, that's going to be only good up to 5,000 volts. We don't have any cable like that rated above 5,000 volts. Everything above 5,000 volts is going to have this some type of metallic shield around it. We'll get to what that purpose is. So when it comes to my percent insulation levels, if my insulation is rated for 100%, and it has to do with clearing ground faults. So if I'm using this in a system with medium voltage, then protective relaying, right? And I can clear that ground fault within a minute or less, then I can use insulation that's rated for 100%. Now, if it takes, say, an hour or less to clear that ground fault, then I need to use insulation that's rated for 133%. And if I can't meet that 1 hour requirement, then I'm going to use 173% insulation. The more insulation rating that I have, the thicker the insulation. So for instance, 133% insulation is thicker than the same value for 100% insulation, and so on. where would we use something like 173% or even 133%? Don't we want to clear ground faults as quickly as possible? Absolutely, maybe, depending, right? What if we're maybe in a steel mill, something like that, and we get a ground fault in our system? We want to detect that ground fault. We want to alert people, but we want to do an orderly shutdown of the equipment. We don't just want to trip the system off the line. So we do have applications where it's going to take time to clear a ground fault, and that's going to affect the insulation level of the cable that we use in the application. So if we look at this one, it says it's 8 kV 100%. So I look in the tables. I have table 315.10b. Table 310.15b, 315.10b gives me the thickness of insulation for non-shielded solid dielectric cables. The next table, 315.10c, tells me the thickness of the insulation when I'm using shielded cables. So for instance, this is number 2 conductor. So if I'm using number 2 conductor at 100% insulation at 8,000 volts, it has to be 115 mils thick. So 0.115 inches thick, the insulation does then. And sure enough, I look back here on the jacket itself, and it says 2 AWG copper, 115. So that's the thickness of the insulation, 115 mils thick. Wow. Now, in reality, do I go and measure the insulation on my cables and then decide whether or not what application I'm going to use it in, measure the thickness of my dielectric? No, I'm not going to do that. What I'm going to do is I'm going to go right to the cable jacket, right, or the tag on the reel, whatever it is, and look up the information on my conductor. And it's going to be UL or CSA listed, and it's going to give me the information that I need. I'm not going to second guess it, most likely, and go out and measure the thickness of my insulation. So I have these tables that tell me the insulation thickness, and also the cable is required to be marked. I have to have the gauge size every 24 inches, and then all the other information every 40 inches. And it tells me specifically in the NEC then in 315 what has to be on those markings, what information it has to have. I've never pulled out a tape measure and gone through and made sure that I've got the proper markings every so many inches once again, but we know that it appears along the length of the conductor. Let's see what else we've got. We've got its MV cable, 105 degrees C, so we know it's type MV 105. ROHS, so it's a capital R, small o, and then a large H or capital H and S. That has to do with the European Union, but it tells me that this, it's where it all originated. But anyway, in the manufacture of this cable, there's a restriction of hazardous substances. So now let's take a look a little bit about this construction. We have the dielectric, but if you can just barely see on the inside of that white dielectric insulation, there's some black. And what I've done is I've pulled off some of this white dielectric insulation, and you see on the inside, there's some black material. That's called the conductor screen. And it actually, when it's extruded on there, it goes down inside and in between, works its way a little bit down in between the individual 7 strands. And what it does, it tends to even out the stresses, the voltage stresses along the conductor itself, because that conductor strand, of course, runs the entire length of the conductor. Now, when I get up above 1,000 volts, electricity tends to take on a little different characteristics. Things that I don't worry about at 480 volts. I start to get voltage stresses. If I were to actually put a lug on this conductor right now, that would not be good. Notice this dielectric insulation right now, the way I've got it cut off, it's just straight, cut it off with a knife. And it's just a nice straight cut, and that's about it. And goes down to the conductor material. Now I would have what? Above 1,000 volts, certainly at up to 5 or 8 kV, whatever application I'm using in this for this cable, that voltage would start to push over the edge, the sharp edge of that dielectric. And what it'll do, that higher voltage will actually move molecules of insulation, and it'll start to move back, and it'll start to deteriorate, break down, I guess, that insulation. And of course, eventually it'll fail. I don't want that. So I have that conductor screen then first over the conductor material. Then the white is the dielectric insulation, and that's the thickest part. And then I'll unwrap a little bit of this metal shield, and I come to another layer of black insulation. Well, that is my insulation shield. Same purpose. It helps to even out the voltage stresses along the top of that insulation. And then finally, you know, we can't keep, I look at it this way. We start getting up into these higher voltages, and we can't keep all of the electrons inside the conductor. Okay, we just can't, it's just hard to manufacture and make dielectric insulation thick enough actually to keep all the electrons inside the conductor so none ever leak out. So what I need to do is I have take this copper sheet that's wrapped around, copper foil is what it is, wrapped around the entire length of my conductor, and I need to attach that to ground. In fact, we're going to find, or we would find in the NEC, I may ground it at more than one point, depending on what I'm doing in my system. So that's going to dissipate any charge that does leak through the insulation in that shield, and take it directly to ground, which is what I want. Also, it does tend to even out the voltage stresses overall. So when it comes to terminating and splicing these cables and so forth, there are some very specific requirements, because if I mess it up, this cable will fail. And I don't want medium voltage cables to fail. They usually play a big part in my distribution system then, don't they? So if I take a look at the requirements for installing this cable, I go to Article 315, Section 30. So it falls under Part 3, installation. And 315.30 says I have to be a qualified person. I have to have, in fact, it says I have to have documented training and experience to perform the installation and testing on this cable. It also says I have to be a qualified person to terminate this cable. Once again, documented training and experience before I can terminate this cable. And then the same is true for my cable joints. Once again, which you and I would probably commonly call splicers. I have to be qualified to do splices. So I have to be qualified to install and test this medium voltage conductor. I have to be qualified to terminate this medium voltage cable, and I have to be qualified to splice it as well. And there's another I mentioned, and I've mentioned this before quite often in these tech talks, and that is the NECA standards, National Electrical Contractors Association, their National Electrical Installation Standards, and they are ANSI approved. NECA 600 covers medium voltage cable installation, splicing, and terminating. And it's a very practical standard, again, once again, for you to help you understand how to do all of this work. Also, it lists the couple different organizations that do certifications for medium voltage cable installation and testing and so forth. When it comes to testing, this dielectric insulation, as I said, is susceptible to break down. And if it breaks down, where it usually often starts to break down anyway, it gets these little, they call them trees. I always say, well, it looks more like the roots of a tree. But I get these trees that start to form and literally crack through the insulation. And if I get water inside of those trees, I've got water trees. Obviously, it's a bad situation. If I have a path for current flow from the conductor out to the outer foil and so forth, I end up with a ground fault in my cable, and I don't want to see that. So there are two types of tests that we often perform to check this insulation. You want to go to your NFPA 70B, the standard now for electrical equipment maintenance, and check that out. But when it comes to this medium voltage dielectric insulation, we might want to do a DC high pot test, where we might apply up to 35,000 volts to this particular insulation, see if any current leaks through. There's another type of test, an AC high potential test at a very low frequency, where we actually apply AC to this insulation and at no greater than 1 hertz, 1 cycle per second. And it's a lower voltage. We check to see what kind of leakage we've got through that at different voltage levels, what kind of leakage we got through that installation. So anyway, different types of tests we have to perform on it. So you want to go to NFPA 70B for that. As far as the ampacity requirements, there are 20 different tables, 20 different tables for ampacity found in Article 315 on medium voltage cable then. And it's all based on the type of conductors you have, whether it's triplexed in air, in a duct, or whatever it is. So you need to go through and look at the different requirements or different applications that you would have before you could determine the ampacity. Also, there are tables in there for temperature correction, just like we would normally have to determine ampacity values. So that, in a nutshell, in a brief nutshell, okay, is medium voltage cable, Article 315. Let's take a quick look now at Article 495 on high voltage equipment and see how that is divided up. Article 495 has 5 sections to it. So the first is some general information, the scope and so forth, and it tells us that other articles would apply. The equipment specific provisions for installing that equipment, as far as maybe spacing requirements and back feeds. And if we have a back feed, we have to have signage there and so forth. That's all covered in part 1, or excuse me, in part 2. Part 3 is on switchgear and industrial control equipment. And so installing any equipment. Now, remember, we're talking about Article 495, equipment over 1,000 volts AC, 1,500 volts DC. So anyway, part 3 is on switchgear and industrial control equipment. And then part 4 is on mobile and portable equipment. And then part 5 is on boilers that operate at greater than 1,000 volts. Righty? The things you have to watch when you're working with this cable, installing this equipment, go back to NFPA 70E and follow your safety requirements. Remember, NFPA 70E is not voltage specific. One of the issues that we've run into, if I'm using this particular medium voltage cable, let's say, in a DC application, then maybe this is my positive, or say, I don't know, positive or negative, whatever. Let's say it's a positive conductor. And then so I'm going to have a positive charge on this cable even after I de-energize it. Now the sheath, if it's properly grounded, the shield, it would take any current flow to the earth. But I need to install grounds on this conductor before I go in there and do any work on it. Right? Temporary protective grounding. It will hold a charge on you and get you in trouble. Those are the high points then when it comes to medium voltage cable, and a little bit about the equipment that we need to install above 1,000 volts. In the meantime, follow your code requirements, take a look at that National Electrical Installation Standard, go to other resources. IEEE has some excellent standards and resources for you on medium voltage cable. Make sure you don't mess with medium voltage cable unless you're a qualified person, then by NEC definition. In the meantime, work safely, whether you're working on a medium voltage cable or whatever you're working on. This Tech Talk has been brought to you by EC&M Magazine once again, and it's part of the Endeavor portfolio of business publications, all righty? So go to ecmweb.com, sign up for premium content, work safe, and we'll see you at the next EC&M Tech Talk.